Have you ever heard something more ironic in your life, class? Without further ado, David Woods.
All right. So, caveat. I've wanted to do this for a long time. And a variety of things have happened that make me go, oh, the hell with everything else I'm supposed to be doing. Let's go full bore into it. 2, we're going to cover a huge array of stuff. But A, you're very smart. But you got to be ready to be quick. Second is you can use all the concepts we've talked about. In fact, we will use lots of the concepts we've talked about in this. And that in many ways, what I'm going to do live in deconstructing systems engineering is what we've been doing with Flash Boys and the rise of high-frequency trading and the emergence of dark pools and all kinds of things that illustrate processes of growth and complexification, adaptation, brittleness, collapse, anomalies, reframing, all this stuff, right? So you have lenses that can help you see this. Now we're going to start long before many of you were born, right? We're going to start this journey with a perspective. And in some ways this perspective is going to address the issue of why should you listen to me at all about this? And the reason is because me, so I don't know, we'll draw this like an eye. In 1979, right, less than 6 months after the nuclear power plant in eastern Pennsylvania on the Susquehanna River had an accident. It's this 3 Mile Island plant. And it was a shock. It was a shock to Pennsylvania, the government, caused a panic in the public. It was a shock to the energy industry, the nuclear industry. It was a shock heard around the world. If you want to get a flavor of it, Richard Cook has a great online talk. It all started with 3 Mile Island. And for me, it literally started with 3 Mile Island. And all of a sudden, a 27-year-old is there dealing with energy systems, systems engineering, large-scale system failures, being asked to design new kinds of control rooms with new technologies, computerization. So I am embedded inside. Remember we talked about perspective? So what am I looking at? I have a special seat to see systems engineering. But systems engineering is a much bigger thing, and I'm seeing, right, so this is way out here, and I'm seeing a portion of systems engineering around how do you build control rooms, right? How do you help people not get stuck? How do you help them reframe when something different goes wrong, right? How do you recognize anomalies? I'm going to use computers to do this. You all think of computers as normal. In 1979, there was no such thing as a PC, right? Internet didn't exist even in the people who they claim was inventing the internet and therefore knew about it even that early, didn't really know that's what was going to happen, right? Hindsight bias says, oh, look how far back this goes. Nope, none of this. So now in this process, I'm inside looking out, right? We talked about that kind of a perspective, and I'm seeing this big process go. And I'm seeing it in the aftermath of a disruption, right? So there's been a big disruption that's happened. And a disruption, interesting, allows us, if we think about systems engineering over time and how it evolves. So if we put time and we put, right, growth, what are our factors? Pressures, faster, better, cheaper pressure, growth, complexification, etc. Right? This disruption very quickly became recognized as a complexity issue. We had made the system more and more complex in the pursuit of efficiency, right? Efficiencies of scale. We can build the energy generating plant bigger, right? It's a lot of money to build one. There's a lot of stuff about a site, etc. Well, let's make them more powerful. Let's make them bigger. And as you scale them up as a big system, systems engineering to some degree is about big. You start scaling it up, it turns out differences in degree start to become differences in kind. Right? A difference in degree becomes a difference in kind. Now, there's another good thing about someone like me having a role about control rooms and a role about understanding this disruption. So one of my roles, I had multiple roles. One was here. Another one I had was looking at the disruption and the kinds of complexities, right? A third role that I had was how to use computers to help it go better, right? All of these things are going on. But in many ways, these kinds of perspectives are not just a local perspective, they're a regional perspective. In other words, you can think of me stepping back and saying, I have a perspective on how all of this is playing out across what? This is a big, tangled, layered network, right? There's layers, there's roles, there's different organizations, you know, the government, regulatory. Remember, it was an internationally disruption event. Everybody around the world started talking about how to do what? Reframe. And so what's interesting is the nature of disruption triggered an explicit international attempts to reframe. Now, what have we talked about reframing? Right? The reframing is hard, right? Right? But a shock event can cause you to go, wait, my view of the world, my model of how the world works is not the way the world really works, and I have to rethink and update, revise, and reframe my model of the world. And that was explicit. Now, every time that happens, and you have adaptation in that direction, you have a counter-adaptation, right? What's the counter-adaptation? If you're going to reframe and revise your model of the world, what are other players in that world going to do? Are they going to go and say, oh yeah, let's do more of that, let's change the world? Or are they going to go the other direction?
They're going to stick to their models.
They want to stick to their models, they want to retreat and retrench. And to retreat and retrench, you have to say, oh, it was just this local factor. Right? Oh, I'm not surprised it was that utility that had the accident. They're second rate. I'm not surprised it was that nuclear power plant design. I'm not surprised of those people, excuse me, and of course they screwed it up. Right? You heard me say, right? People who no one thought this could happen. Their model of how failure could threaten the viability of nuclear power plant, creating a catastrophic event, right, did not take into account the combination of small failures, misjudgments, because it got into a state that no one in the operational world knew it could get into. So it did really require a new direction. But that new direction very quickly, even when you have a reframing a new direction, slides backwards. So it goes part way and it slides backwards. This is all covered in behind human error and things. But for us right now, it means I got to see what was going on relative to this point in time. Right, the shock. I could see backwards into systems engineering's growth, and I could see forward as it struggled to readjust, and we can keep seeing forward over the last 40 years as systems engineering has adapted. So what's our topic for today? Our topic for today is very simple. How has system engineering adapted to cope with complexity? And The irony here is that systems engineering develops in ways that creates complexity because it wants to do big things, right? Gotta do big things. And in the process of doing big things, you're probably gonna run into complexity, and you're probably gonna want to cope with that complexity, and your coping mechanisms may not really understand the complexities you're coping with, or how your coping mechanisms are creating complexities, right? That's the stuff we've talked about in an adaptive dynamic world, right? It's not static, oh, these are the two complexities, I can deal with these. All right, got this. I think we're gonna have to erase it since we're focusing on one board. And move on to the next step. So let's talk about how you got this? All right.
I have it saved as well.
Okay. So what I want to go to now is how did this work? And when I say I had a seat, I could tell you stories, which are fun stories, but not really the scope for today, about me confronting and constantly feeling like I was in The Princess Bride, even though The Princess Bride wasn't made yet. You keep saying these words, and I don't think you know what they mean. Because I was a fresh perspective, looking at systems engineering, being asked to do something new in systems engineering after a big, shocking surprise event. So my claim to you about why you should listen is because I had a seat. I had a perspective. In fact, I had a regional perspective as well as a local perspective on what was going on. Now, of those 50 people out there, many of them have a perspective on systems engineering. They have experiences in systems engineering. They were in a position having a perspective that was local, as things happen, for example, in aviation, air traffic control, maritime shipping, other kinds of worlds. It will be interesting how this account of my journey, right, over 40 years that influences safety, the start of joint cognitive systems, the start of resilience engineering, fits with other people's experiences. I think there's some self-selection of who's listening in are going to tend to have already, right, been connected to these sorts of ideas and trends. But we want to show how there's been an arc where our unit of analysis, the unit of adaptive behavior we're looking at is systems engineering. Not a nurse, not nursing, right? Not people in an emergency room handling a mass casualty event. Systems engineering. In high frequency trading, it'd be like saying, let's look at dark pools. Right, this sort of big, funky, multifaceted, lots of units and tangles within it. Let's look at it as a unit of adaptive behavior. And we want to look at it relative to complexity. And how did it try to deal with being big and being under pressure, right? Because remember, what do we say about any unit in the world, any unit that's going to be somewhere in a tangled, distributed, layered network, they're under pressure. Pressure comes from other parties and their goals. Why do we talk about other parties and their goals? Because, right, there's always other players seeking advantage. They're adapting to get advantage. We also have finite resources. And we have continuing change. We just started with an episode and a point of change. Conceptual change, change on many important dimensions. Now, before we get into this, I want to remind you of my special observations of what was going on happened because 3 Mile Island put the nuclear power industry into a coma. Like, think of your medical mysteries or your detective mysteries where one of the parties isn't killed but is in the hospital and they're waiting for them to wake up to see what information about who was the culprit, right, what's going on. Nuclear power went into a coma. But for me, what was lucky, nuclear power didn't realize it was in a coma. It took them about 5 years to go, oh, wait a minute, we're not building any more plants. We're not going to build any of these control rooms you're designing. We built one in a couple years that was fully specified to be built. They did build the alarm system we created, which is still completely unique, but only in one plant in Switzerland. It's still there. And now there is a caveat, a big caveat, and that is the Coma did not apply to France and Japan. France, right, caveat, we don't have to go into it, but France has made a commitment into nuclear power as fundamental to the state, and so it's a different storyline for them. Japan had similar reasons of a commitment, and that ended. That became precarious over time because the rest of the industry was kind of in a coma, and that ended with Fukushima. The tsunami, they hit the nuclear power plant, right? As well as Sendai and other places and killed tens of thousands and wiped out the nuclear plant. So take the Coma, right? And it's still in a coma. It's still constantly, periodically we're going to come out of the coma and get going again. We went into a coma. Why was that great for me? Was because we had money and time. We had a little relaxation on the schedule to design a computerized control room. So we could do it completely new way. Very ambitiously, conceptually, what was easy to build in those days. So we were actually trying to do systems engineering. I wasn't just watching systems engineering. And so we had this window of a couple of years where we could do things that a normal schedule would have never allowed us to do. We would have had to stick with the traditional mechanisms of systems engineering. Doing things differently wouldn't have been possible. So that relaxation's allowed us to do some things different. One more piece of history. At the same time, I got to be part of the team designing the control room for what was called the Clinch River Breeder Reactor. All right, all of you up on your nuclear power, nuclear weapons. A breeder reactor makes plutonium. So it's a dual purpose plant. It makes energy and it can produce, right, materials that can then be used in weapons. And it was very controversial in that era. And it was never built. But it exemplified what was the older systems engineering as we were trying to do something new and different because of the shock event and the window of opportunity to reframe. Right? I was part of something that was doing it in the old-fashioned way. Now you would call what we were doing old-fashioned too, with all the fancy tools you have. But it actually wasn't as old-fashioned as you might think, even though we didn't have the tools you have today. In fact, it was kind of amazing we did as much as we did without any of the tools you have today. Now, at some points I'll refer back to what went on in my experiences going down to Oak Ridge, Tennessee, and trying to plan out a new kind of plant. And it was a new plant. And so it's very interesting that I had experience doing something brand new, right, in nuclear power. So we understood how to build these things, but now we were going to do a different kind of nuclear process with a different kind of coolant. Instead of water, it was going to use sodium. And we don't have to go and look up, but having liquefied sodium at high pressure and high temperatures is a very, 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 did I say very dangerous, hazardous thing to play with. And many years later, run into one of the other designers who was older and more experienced, and he said, thank God we never built this thing, because it was sort of the traditional way to make things big and deal with risk kind of on steroids. So I got to see sort of the best worst case of systems engineering gone amok by the standards of the day. So again, this is my source of validity, not classic studies and models and things. Observing and participating in these trends. So how does this work? So systems engineering, all right, has a technique. It's trying to do something big. So assume there's some kind of bigness to it, and it's under pressure. Right? We've already indicated in these windows and glimpses, it was pressure or relaxation of pressure that opened other possibilities. Okay, so how are you going to do something big and you're under pressure? Well, the technique is pretty simple. You decompose it into parts. Right? You break it into parts. And what do you do with the parts? You go, you get, well, we'll do it in modern terms. You get the hardware. You get the software. You're in India. All right? You generate the requirements and send it to India. India does something and sends it to the hardware people, who send it to the software people, or the software people send something to the hardware people because they constrain the hardware and the hardware constrains the software. But that all depends on somebody actually building something detailed. Oh, because there's subparts, right? There's parts and subparts. So systems engineering takes something big and says, oh, there's this part. Oh, but that part then becomes these parts. Right? And then this part has to connect to this part, but those two things go together to make this part. And then, but that has an influence on this part over here, which depends on this. And it has a different version of this over here, which fits here, but that's related to this down here. Wait a minute here. Can you really decompose it into mostly independent parts? Are these independent?
Class A? Those independent?
Independent. What?
I'm just asking them the answer.
Oh, can you decompose it into independent parts? Well, systems engineering assumption was almost. But boiling this all down, the answer is, and the classic thing is almost. So we'll check. Oh, and I forgot, one of the seats I had were the people who were checking. Because where did we get money to do stuff? We got money from safety. And the money on safety had to do with risk analysis. And what did risk analysis do? Risk analysis was trying to check, did we cut this into pieces that are mostly independent? And so they worried about things that would violate a pragmatic independence assumption. And we're going to talk about two of them. Now, before we dig into those, I want to read you something. 3 Mile Island happened in 1979. Right? I was young and skinny, and if you think I talk now, you should have seen me then. So, the first modern risk analyses were being transferred from military systems. We watched Oppenheimer, right? All that translated into how do you measure the risk of things going wrong in nuclear weapons programs, all this stuff. So they developed techniques for risk analysis called probabilistic risk analysis and other things. And they now migrate into other forms of engineering big systems. So a year before the accident, there is a review of the first major risk analysis study of nuclear power, commercial nuclear power plants in the Western world. Soviet Union is a completely different story. And they then, so they commissioned the risk analysis, which of course found that the probability of anything serious going wrong was remarkably low. It was, I don't know what you do in lean. How many digits do you do in lean? How many digits? How many? 99.99. How many 0.99s do you want to do in lean? I don't know. But in nuclear power and risk analysis and things, it was 10 to the minus 8. Oh, the probability of things going wrong is 10 to the minus 8. It's really, really, really improbable. Now, having been there and watched the sausage being made, did I ever believe for a second those numbers? No. Well, smart engineers actually didn't believe them either. All right, so this is from a review of that risk analysis of nuclear commercial power called the Lewis Commission. All right. We found a number of sources of both conservatism and non-conservatism in the probability calculations. These are difficult to balance, right? It's, we have an inability to quantify human adaptability during the course of an accident. Regulatory influence, in other words, an outside influence on the choice of uncertain parameters, and a nagging uncertainty about completeness, and an inadequate treatment of common cause failures. We are unable to define whether the overall probability of a nuclear accident is in fact high or low, but we are absolutely certain that the error bands are understated. We cannot say how much. What did that say? It said, you tried to check on how independent this is, and if these things have been elaborated and done to engineer the big system so that independence is true. It didn't take independence for granted. It tried to engineer independence in through redundancy, diversity, various checks, that we would be able to have a very reliable system. 10 to the minus 8. And they came back and said, a year before the accident, what are you talking about? That is so uncertain. You're making so many assumptions and guesses about how things will work, right? How will people respond to it? How we're making judgments influenced by stakeholders who want to build plants because they want to make energy. This was supposed to be the future. It was supposed to do lots of good things for energy and for our access to energy. And what we are certain of is we are uncertain. That's one of the things that's been in our discussions about, right? Trajectories of change, velocities of change. It's uncertainty is ahead. And sometimes the signals go that those uncertainties are bigger or those uncertainties are different, but there's more uncertainties. The more uncertainty or the more uncertainty is changing, the more you should value investing in adaptive capacity. Because the thing you can be certain of is that you're going to need to adapt when those uncertainties start to become less uncertain. They start to reveal themselves in new ways, the way the system now works. Okay, don't need that anymore. Like the old days with overheads. So, now, sneak paths and common mode factors. That old one called it common cause. Cause is a bad word in a complex network. You're fooling yourself when you say cause. You're not understanding the world. You're tricking yourself to think you understand the world in ways you probably don't, just like that report from the Lewis Commission. So what's a sneak path? So you engineer the system in this network, this decomposed network, and then you put it back together. When you re-aggregate it, you're checking to say, hey, yeah, we got independence. Right? For a big thing to go, a top-level event to go wrong, all these little ones have to go wrong. Because we have safeguards, we have redundancy, we have diversity, or even if there's a backup for this, even if we lose this. They build in a lot of stuff so that a problem in one place can't build into a problem that would create a catastrophe. In the same way, the critical digital infrastructure, right, can only grow and underpin all kinds of valued services if we are fault tolerant. Lots of things can go wrong and not significantly impact the vital service or the valued service. And if it's a valued service, it's not long before it becomes a vital service. That's called the slide to criticality, which we haven't covered yet. So, what did they worry about in the systems engineering to get independence and therefore high reliability. Right? And in the risks analysis and other checks they did to say, did we really pull it off? We have to convince people we pulled it off. Well, they would look for sneak paths. So how can something sneak around our defenses? Sneak paths comes from electronics, circuit design, and they would talk about sneak paths in circuit design and how they're hard to uncover because they're, in effect, a complexity effect. Right? You may try to trace all the paths, think you have a complete model of all the paths where all the energy goes, et cetera, et cetera. Ground faults. You ever run an electronic system and it doesn't work and you have to track down ground faults? If you ever had to do this, you hope you never have to do it again because it is very difficult to understand a complex system and trace these things down. Did you ever have to do that?
I once had a Toyota Tundra that would accelerate every with the beat of the windshield wipers.
Thank you for a concrete example of the sneak path. I was trying to think of a concrete one that would appeal to you, and you did it for me. Thank you so much. So sneak paths, they come from, and so when I started in engineering 45, interacting with them, the crazy cognitive psychologist who studies the brain and perception and attention and shows up having to do all this stuff. I mean, this is all crazy. I'm the one explaining systems engineers to engineers, but that's what happened right from the beginning. That's what fresh points of view can kind of do. They started to generalize sneak paths as a term of use to say, oh, we missed something. There is a hidden interaction, a hidden interdependency that can short circuit, in quotes, right, are otherwise really reliable, right, design because we made all these things independent so they can't combine in ways that are very likely to produce an overall catastrophic event. We have high reliability, 10 to the minus 8. Can you believe that people would actually say to Congress, to the public, we are so safe, the risk of a failure is 10 to the minus 8. Do you understand what 10 to the minus 8 means? You've been in a lot of math classes. Are you the general public? I don't think they understood 10 to the minus 8 either, but that's what they kept saying, 10 to the minus 8. Engineers can be a little weird. I'm not speaking about you, of course. Wait a minute. I am speaking about you. You're systems engineers. Uh-oh. So we're giving you a kind of history lesson on systems engineering, which is what you're supposed to do. Oh, wait a minute, don't worry. We'll get up to now. It gets worse. Just in case you thought there was going to be a happy ending. You should know what the ending is. You've been in the class long enough. Oh my God, we're going to run out of time. Common mode. That's where one thing goes wrong that takes out several things that you're count on so that things don't propagate into a bad thing. Have you noticed in our incidents there are common mode effects everywhere? Why? Because of the extensive interdependency. Something can go wrong that affects the ability to provide important things other places, and so we end up with a loss of valued services. So the difference in the old days was these were assumed to be, so we assume we can do this and achieve independence. We can answer this question, right? The assumption is by decomposing and reaggregating in the right way, we can answer and assure the question that we're almost independent. And we have checked sneak paths and common mode factors. So the assumption here is they are limited, right, and traceable. That Lewis Commission quote says, even the engineers then suspected that's not true. And in the aftermath of the accident, the major diagnoses that echoed around the world and created consternation and an effort to reframe was because they recognized that you can't guarantee independence, that these aren't limited, these aren't easily traceable, tractable, discoverable. We can't completely characterize the interdependencies. even in a system like a power plant where we designed the whole thing, we built the whole thing, and it behaves according to the laws of physics. So if we couldn't do it there, where we have the laws of physics underpinning everything, do you think we can do it with modern digital systems? Can we do it as we scale up and have effects that have regional, national, and global span? You know, Lewis's commission's warning here says, whoops, wait a minute. The one thing we can be certain about is it's how we're going to do this in the future is uncertain. Uncertain. Now, we can talk forever about these and how they play out, but the key we want to deal with here is there are limits to this. Okay. Now, let's see, what else do I want to say about this? Coma. Oh, okay, I know what. So, now, remember, systems engineering suspects that this story isn't true. Right? So you have events like 3 Mile Island, and the question is, as events occur, as shock events occur, as changes occur, new technologies, etc., how does systems engineering adapt? How does it adapt? Because it adapts, right? It's a unit of adaptive behavior. It has a limited range for its adaptive behavior. We saw that expand after the big accident in '79 as they considered possibilities and introduced dramatic changes in how you run nuclear power plants. It also constricted, retracted, because many parties said, oh, no, we just do it this way. Remember, that's that sort of, right, we adapt to revitalize. We didn't know they were in a coma, but we were working really hard to revitalize it in a new way. At the other time, others go back and retrench. Right? And the retrenchment was, guess what the word would be? We're going to go backwards and say, everything would have worked great if you had just done everything according to the rule book. If you had worked the rule, if we make sure they work to rule, if we put more pressure on them to work to rule, if you just work to roll, right? If everyone just follows the plan. Oh, excuse me, sir, the plan didn't, it was the wrong plan. It misunderstood what was really risky and how bad things could happen and how we really handled them. We built a new plan. And the new plan is sure to encompass all possible ways things can break. We won't get into why they thought that. There was some reasonableness to it. What did Emily Roth and I do in the 80s and early 90s is we ran various accidents. We looked at real accidents that occurred, and we highlighted the inability to handle everything that could go wrong in a nuclear power plant, because many things went wrong in nuclear power plants that weren't the scale of 3 Mile Island that scared everybody in eastern Pennsylvania. And what we found very quickly is you can't work to rule, work to roll, and work to plan and solve all the problems that happen, right? Surprise is omnipresent. So they wanted to go and retrench, and that's a trend. So again, caveat for the moment, I am describing from my perspective, local and regional, all right, aspects of systems engineering as an adaptive unit, and ways that it adapts, ways that it adapts to retrench, ways that it adapts to move forward. Others will say, oh, but it's a really big thing, systems engineering, and sometimes we succeed to build big things. But what is now true of systems engineering of big things? What's gotten big too with our systems engineering? Big pressure. The big pressure to be faster, better, cheaper. It was there before, driving scale and complexity, discounting the trouble to operate and diagnose breakdowns in a really complex, interconnected, interdependent system. Now, it's the fresh, faster, better, cheaper pressure has increased, and so engineering now will get dispersed. The decomposition now gets even more into a dispersion into different organizations. So where would you look at this today? I guess you can watch John, I'm blocking on his name, the comic. Oliver, thank you. John Oliver doing a thing on Boeing. But don't, and yes, it applies to the 737 MAX accidents. But if you want to see this from a systems engineering point of view, you want to look up the problems that arose with the 787, right, the Dreamliner. And Oliver covers some of those in his piece on Boeing, which is a reasonable piece on Boeing. And its inability to do effective systems engineering under big, faster, better, cheaper pressure. And that applies tragically to the genesis of the 346 deaths in the twin accidents in 2018 and 2019. But I think for your perspective and for connecting it to people that you will work with going forward, it's actually more effective to do it with the Dreamliner and all the problems that arose. So they were doing something new, but they were under faster, better, cheaper pressure. So what did they do? They outsourced things. So there's more parties. Now, you could outsource things and organize them in effective ways, right? But that means you have to put a lot of energy and effort into the integration function. How do you put these things together? You have to put a lot into the coordination function of all the different organizations and the different parts that are going and have to be put together to create a whole. You have to think about emergent effects. You can't just think linearly that these will add up to the total system. We could do the F-35. We could do other ones. There's less information on big Defense Department things that run way over budget, less functionality, other kinds of problems. We could do the Marine Corps Osprey helicopter. We could do, there's a bunch of these different things of systems engineering where you eventually get something built, but there's a legacy of problems. But the Dreamliner is a good one. It's accessible, there's general reports about it, and it reminds you. So what happened to me last week? It's always this way. An engineer calls me up and is complaining about doing systems engineering, right, in this dispersed way with lots of outsourcing. We got hardware, we got software, we've got energy plants, not nuclear. We've got outsourcing to India in order to have things cheap. What do we have? What is he describing? He's describing a high cost of coordination without any good mechanisms for controlling and synchronizing across the different players doing different interdependent parts of an upgrade of systems to this energy plant. And it gets, in some ways, very detailed. And in some sense, it's a classic big story of fragmentation, high cost of coordination, roll retreat, because if they come back and put a lot of pressure, work to roll, work to rule, work to roll, you can now defend yourself from problems by saying, I did the specification of my role. The communication I got from those people said, you just do this, and this goes to this, and these things go to that. The fact that they didn't remind me that they changed the hardware, and the new hardware numbers the ports in the opposite way. The ports numbering system changed because they bought the part from a new company and they didn't tell the Indian engineers who didn't tell the software people who didn't know that the hardware had changed, and the hardware people didn't notice it changed in a simple way that had the numbering system backwards, so when they got to test the plant stuff, oh, by the way, nobody went to the site to see any of the stuff that was arriving that they were going to have to put together under high pressure over a short installation period where they were supposed to test it and it was supposed to work. And now who's to blame? The company that owns the energy facility, or the engineering outfit that was supposed to do the upgrade, or the people who decided it should be outsourced and we should have more parties with still no good investment in coordination, synchronization. And so what do they end? Nobody pays for anybody to go to the plant to see what's going on. So they show up for the test and they find out that stuff is backwards. So what do you guarantee with high cost of coordination with this fragmentation? You guarantee lags. Lags aren't a surprise. Longer, right, testing and installation, longer cost to it, less profitability for the parties, less productivity for the parent organization. The lag is guaranteed. Does anybody see the lag is guaranteed? No. Because they're all too busy saying it will work so great. And sometimes it kind of works so great. And we're meeting all these things. But what do we find is most of the time we're fudging the numbers up here. Because it didn't work so great. Because cost of coordination was high. Or we push those costs onto one group and pretend it wasn't over here. When the total cost of doing it, if you integrate across all the parties, but guess what? Your creative accounting now can show it's all okay because they lost money as a subcontractor, and you're subcontracting to her lost money, and subcontracting the next person lost money. Now, could you do specialization if you saw this as specialization and put it all back together with an effective integration function? And the answer is yes, you could, except guess what we show? Remember we said there are two comprehensive theories about how this all works? My theory of graceful extensibility and John Doyle and others, diversity-enabled sweet spots. Well, what does his math do? His math says, oh yeah, let's take a system, let's take systems engineering and think about it in its best way. So you're going to specialize in one part of this, and you're going to specialize in another part of this, and you're really good at your specialization, and you're really good at yours. Right? We're going to say finite resources aren't crippling you. Faster, better, cheaper pressure hasn't isolated you. Lines of communication are great. But in your specialization, you're making trade-off decisions in a way to best balance over the set of trade-offs for what you're supposed to provide. And you're making trade-off decisions about what you're supposed to provide. What's the emergent thing have to do? It's not so simple integration. Plug these in, adjust a little bit. No, it's another substantive layer in a network. And why did we start with systems engineering? To show you can do this tangled layer network all the way down from, in biology, a cell. Right, all the way up to dark pools and financial trading, all the way up to systems engineering as an enterprise, building big things. And how you see these different kinds of interconnections come together. So I fear that this is really a two-class talk. Is coming true. So here's the situation. This whole process in today's world, given growth and complexification, given the kinds of tools, given things that are valuable tend to become not just a valued service, but a vital service. So losing it takes down things that matter to some stakeholders a lot. Not necessarily killing people, but really so important that key things you have to accomplish in the world can't be done. Right, so that growth and complexification we've talked about means this is unstable in today's world. And if they can't step out of their perspective and see that their adaptations to growth and complexity are limited. The range of adaptive behavior is limited. Retrenching doesn't solve it. You're chasing the problems that are created at an emergent level. Right? You have to not get trapped in linear thinking, or that it's mostly decomposable and reaggregatable, and it's just a collection of stuff with some integration and some double checks on funky interactions. Now, you can say that's a little bit unfair, and I would say, yeah, a tiny bit unfair, maybe. It's essentially what's going on. Are there exceptions? People, places that try to overcome these things? Probably. I haven't been in one yet. I've been 45 years, I've been around a lot. Now, it turns out I have some friends who think they have exceptions. And so how did they try to overcome this? Remember I said there's more adaptations? So the forward-looking adaptations are and I'll give you a new hot one. What's the new hot one? Digital twins. Sorry, I went on the other board. I give up. Somebody can write. We're almost out of time, so it's not going to work anyway. So a bunch of people have said, hey, we can build new techniques for systems engineering that recognize the complexity because we're going to put a bunch of energy and we've got new techniques to help you find all the interdependencies. You can map all the parts. Ironically, just as an aside, one of the post-3 Mile Island fixes that was supposed to happen as a regulatory requirement for the industry was to map all the interdependencies. I swear to God. It's almost completely forgotten that this existed. You were supposed to create a system that would dynamically track interdependencies so that when things were down for maintenance or things broke and were tagged out or whatever, you could check whether you had sufficient backup. Did you have sufficient backup to have high reliability? Did your assumption of independence, right, as engineered, as tested, as analyzed, did it hold up? Because things are going to be down, things are going to be broken. By the way, why did we think the breeder reactor design was classic systems engineering on steroids? Because when it was canceled, I'll just give you one statistic. Basically, because it was so controversial to make it super safe, every system had an extra redundancy, or an extra backup, or an extra this. There were so many parts and so many interconnections. It was like the absolute peak of trying to produce active safety and creating maximum complexity. And so one of the guys said to me years later, ran into him and he says, thank God we didn't build that. Do you realize when the plant was canceled, we had 30,000 sensors. The plant was going to be full of 30,000 sensors. How many would be miscalibrated? How many would be out for test because of problems? How many might be off in an accident situation, misleading the operators trying to figure it out? The diagnostic challenge of trying to operate in a world where what's the first and most probable explanation of anything that goes wrong? Bad sensor. But when it really went wrong, there would be sensors telling you it really went wrong, and ones that were just bad sensors. It would have been a diagnostic nightmare. And that was only one aspect of all this stuff. It was mind-bogglingly crazy to try to design it this way, and thank God we didn't build it. Whether you're opposed to this stuff or not, it would have been an engineering catastrophe. That was me or not? But
That was me.
oh, okay. So mapping all the interdependencies is a good idea. Should you invest in mapping more interdependencies? Sure. It's always great. Can you do enough? No. That's what the people who do critical digital infrastructure found too. You can't understand all of the interdependencies. Growth and complexification that inevitably accompanies growth means it will have hidden interdependencies. That's why the most common expression in an incident in critical digital services is, I didn't know it worked that way. Not it broke that way, it worked that way. Right? And in the after action reviews, I didn't understand how it worked. That this would affect this. And remember, in these worlds, it's an issue of overload. It's not an issue of failure. It's an issue of how, yes, there's some things that can break. Yes, there's some things that can be out. But it really relates to what are the changing demands over time and how do those create high load, and what's your responsiveness to handle load. The system is designed to be responsive to handle varying and high load. But load can combine in ways and your responsiveness can degrade in ways that come together to say you can't service the load. And then what happens? When you can't service the load, you stop servicing load, which means they have to service more load. And they run out of capacity to service more load. And when they can't do it, they dump it over here, and then you have more load to deal with it. You can't deal with it. Oh, and then you figure out what drove that, and you're ready to come back, and all these people want to use the service because they haven't had it for 3.5 hours, and they're all busy to get on with their priority tasks. And so when you try to start your stuff up, right, you can't do it because it overloads what they're trying to start up, which overloads what they're trying to start up, and the next thing you know, it's now out for 8 hours because you overloaded on the recovery side. It's all about the dynamics and changes in load. What you can do versus what you can't do. That turns out to be a secret ingredient, once you understand that, about how to escape the limits of this. Oh, yes. This is all going really well. I only had 40 minutes. So, these don't really handle the instability. They're nice. Oh, I didn't get the digital twins. I guess I could. Digital twins is you build a simulation of the complex big system so that you can test everything in the digital twin, and it's so realistic and captures so much of the real world that it will tell you if things you're doing are going to turn out, or upgrades you want to do, or changes, or whatever, will end up working as expected, or not working as expected. So you can modify and adjust. It's supposed to be a way to adapt a big thing that you can't completely test in advance, so we'll test it by having a digital twin. Oh, wait a minute. What's the constraint on the adaptive universe? What's the constraint on that? The big constraint on the adaptive universe. Where was I in all this? Am I an outsider? Was I an outsider? No, I was working a job that had to deliver stuff, right? I was working a job that was supposed to produce results from studies that could be used. I was supposed to figure out how the world worked. I was supposed to get a job at Ohio State by publishing in journals so somebody would hire me as a professor. I had stuff I had to do. I'm in the world. I'm in the network. The rules, the constraints, the dynamics of the adaptive universe applies to me just as much as it applied to the traditional systems engineering. We can't stand out. I'm not standing outside understanding it. I'm inside. I've got an inside out view, and I have the ability to step out because of some positions I take in the network, the tangled layered network of systems engineering, and I can see regionally what's going on. I can take a regional view. Oh, by the way, I can take several different kinds of regional views, and I can take several different kinds of local views. I could understand something about systems engineering, not because I stood outside in a semi-omniscient, right? The semi-omniscient outside observer is just like that independence assumption. It's fictional. It's completely fictional. It's comforting. It's nice. It's great to pretend. It's powerful. And, you know, like we play lots of make-believe games. Unfortunately, when it's things that are valuable with real consequences and real things at stakes for real people, we shouldn't play those kinds of games. They're for little children. So the constraint is you're never outside the constraints of the adaptive universe. All the rules and things we've talked about apply to us as we're trying to figure out ways to handle those constraints. We have to have a way to deal with the constraints while we're constrained by them. That's the ultimate paradox that makes people look and go, no, Dave, John Doyle, the world can't work that way. There has to be some way to stand outside and understand it all. And the answer is no, there isn't. I mean, this has been a debate in biology since Darwin. Forget all the other stuff. The debate there is, are we in it, or can we be outside it and understand it? And the answer is, we are in it. We are in it up to our eyebrows. You are in it up to your eyebrows, and you have 50 years to be in it up to your eyebrows, at least. I don't have to worry so much. Sometimes there's benefits to getting home. 10 minutes, eh? Okay. So we've done an adaptive history of systems engineering. How would we reconstruct it? Well, first off, I want to summarize my deconstruction as, wait a minute. Resilience engineering is Brad. You all studied Brad in the story of high frequency trading. What did Brad do? Brad noticed anomalies. Brad didn't let anomalies sit. Brad said, wait a minute, anomalies have to be explained. Anomalies are an opportunity for updating models. Oh, wait a minute. The more he investigated the anomaly, the more it was not updating the model, it's revising the model. Oh, wait, the more he investigated and figured out and built a team and started doing things, it wasn't just revising, it was reframing. That he understood the whole industry to have moved in a fundamentally different way, with new players, new relationships, new risks, new sources of advantage. Who was getting taken advantage of? Who was getting an advantage? What was the source of that advantage? Running through this as a resilience engineering lens on my experiences of systems engineering is being Brad. Right? When I said this, I felt like the Princess Bride before I knew there was the Princess Bride movie. I was being like Brad. Why could I be like Brad? I was an outside perspective. A fresh perspective is one of the ways you avoid getting stuck. What's wrong with systems engineering? It's slow, fragmented, and stale. Even when it's done well, it's going to be too slow. It's going to be too fragmented, and it's going to be unable to revise fast enough to keep pace with the change going on in the world. Right? The rate at which change is happening, right? We're not able to match the velocity of change in the world. And I have a series of slides to show you about that, which would have been a perfect ending, but I need 10 minutes and I don't have that. So I'm going to leave you with a teaser for Tuesday, since we're behind. Sorry, Mike. Tuesday's plan just changed again.
I'm astonished.
So let me point to you, there's an escape route. Right? And this escape route has been in front of us all the time. It was in front of me for years before I saw it, through all these experiences. And the escape route is you start to regulate how you behave at whatever unit, at whatever scale, whatever layer, based on how you approach saturation. The key thing here is to see everyone has a limited range of adaptive behavior. Your adaptive capacity has limits, it's bounded like everything else. And so you need to be able to stretch at the boundaries. In other words, you have to have something to deploy, something to stretch, some extensibility as you start to approach saturation. The current designs tend to wait too long and have to act too big when you get near saturation. You know, ultimately they wait till you're saturated and then it quits, right? And then throws load someplace else, or that load doesn't get serviced, which, because it doesn't get serviced, creates load for other parts of the system, right? So by going big late in approaching saturation and responding to saturation locally in a way that doesn't take into account other interdependent units with you, you propagate trouble. And so the secret sauce starts with saturation. It's about the approach to saturation. It's in the control theory textbooks, but it's done in a very narrow way. And so whether it is a workload, cognitive load issue, or whether it's a control theory issue on building control systems, I can point many different threads that come together. They all come together with this new reframing and say, there is a pragmatic general way out. And it starts with what happens when we approach saturation. You can take local views or regional views and say, the local view is, what do I do? What am I part of? What happens when we approach saturation? Who are we connected to? Who are we interdependent with? If we step back and take a regional view, what happens when parts of that group, that neighborhood, approach saturation? What does the formal theoretical constraints on this universe tell you? You have to have some extensibility. It has to be graceful, right? Smooth transition as load goes up. You have to have some graceful extensibility. But the constraints of the adaptive universe apply to you trying to be more intelligent in how you respond to approaching saturation. Right? So you have to have some graceful extensibility. You can't have enough by yourself. Right? Because the rules apply to you, which means you need help. What happens, work to rule, work to roll, work to plan? You don't get help. The story I got last week was some people retreat into their role and don't stretch across roles to help when saturation occurs. And they exacerbate the problems, delay the objectives, produce lag, extra costs. The people they rely on are people who go outside their role, recognizing there's other interdependent roles, and call up and go, hey, you know the numbering system, we bought new hardware and the numbering system's the reverse. Did you take that into account? And somebody called up and said that. And we're like, what? Nobody told me they changed the hardware with a different numbering system. We assumed they had already taken whatever they had changed into account. Whoops, maybe that's why we're having trouble. I mean, sometimes it can be some apparently simple thing you would just want to call a bug or a glitch or whatever, but it isn't. The messiness is always going to be there. So you want people who stretch across roles, not only stretch within their role as saturation happens. I want you to help me when I'm saturated. And I want to help you when you're saturated. And if you build that relationship across all of the interdependent units, you've built reciprocity. And that's what Eleanor Ostrom said was essential ingredient to make actual large-scale systems work in the face of complexity. Not what they do. Because they don't build reciprocity. They don't have reciprocity in their model of the world. They don't have perspective in the model of the world. All of these things that we add to have a good model of the world don't exist in that kind of classic approach. Well, actually they did, because one of the big changes into 3 Mile Island was, oh, organizational and human factors are really important. Would you give me a number for them that we can put into our risk analysis to say whether we're still going to be 10 to the minus 8? Right? I could show you my scars from fights with these people. They were bitter. They were screaming. Did you think I screamed and cursed? This is calm. Right? Because, I mean, these were fights. And we thought about these things as that, you do it wrong, you're going to kill somebody. You're going to kill somebody, right? You do it wrong. Oh, that's right. Who are we talking about? Tesla. Yeah, this is the driver who did it. Yeah. Or in general, well, we won't go into cars more. We don't have to just do Tesla. Because the industry has some instabilities. So the question in the end becomes, we're going to end with this last point, and then we'll pick up on Tuesday. Also, questions, comments, things are encouraged and would be very much appreciated, even if it slows down the schedule, Mike. So people online, people here, anything you want to ask, anything you want to challenge, get it together, bring it to class Tuesday, send it in advance, whatever you want to do. There's one more constraint of the adaptive universe I got to mention before you run. What I'm going to lay out on Tuesday is reconstructing systems engineering for complexity. Right? We can do it. We're in the process of doing it. Resilience engineering is the heart of doing it. Everybody needs to do it, whatever they want to call it. They need to do it because the world is different. What's our problem? Our problem is the rules of the adaptive universe apply to us. The fact that systems engineering is stuck in an unstable mode, right, doesn't mean they're going to just jump up and say, oh yeah, these people are right, we need to do systems engineering different. We'll just start doing it different, right? DoD will start doing it different. Oh, they're not going to start doing it different. Cars, they're going to start doing it different? Well, there are opportunities to do it different. Some parts are locked in and retrenched or captured by their model of the world and not have some of these characteristics of the adaptive universe in their foreground. But we have to provide a path. We don't provide a solution. This tries to provide a solution. Oh, 10 to the minus 8 reliability. No. We're not providing solutions. Our approach doesn't provide a solution. The people who are going to hire you want a solution. They want to know how much the solution costs relative to not doing a solution. Right? That's being stuck in that old view. It's unstable. You're going to bounce from one surprising effect to another surprising effect because you're lost in the trade space. You're lost in the trade space. You have a restricted range of adaptive behavior, so you respond to one event, you go this way, and then the next event you go that way. That's called bang-bang control. That's how a new teenager drives a car. Oops, I steered too close to the side of the road. Whoa, now you're in the lane of the other traffic. Oh no, go back this way. That's called bang-bang control. That's really bad control. That's as bad control as you can get. The only worst control is where you just crash the car immediately into a tree. Right? I mean, that's not what you want. That's what this is now. Bang-bang control. Bad. Unstable. Not a state you want to be in. A dynamical state you want to be in. So how do we move them from there? Well, we don't provide solutions. We provide paths. Right? We try to change the constraints so that the kinds of adaptations that play out add together in a way that they will tend to find good operating points and change to find good operating points in a multi-dimensional trade space. That they can dynamically navigate the trade space. And they have to do it by the emergent result of the interactions of many units of adaptive behavior. And if that's what people want to say, Dave, you're an optimist. And I'll say, yes, I am. And I have proof of concepts in biology, in social systems, in cognitive systems, that it can be done. And we have pathways to help do that. What constraints to impose, what constraints to relax, right, that will allow groups to develop and change over time. And that's called guided adaptability, continuous adaptability. And we have, guess what? The best example of people actually doing it is critical digital services. Otherwise, they wouldn't work well enough for you to rely on them in every phase of your life. So we do a proof of concept. And Tuesday, I will tell you more about how to do this.
Excellent. So thank you, David.